I have, let me bring the photo here. I have a machine, and this is a machine considering that it's moving. It's this is simplified version of some machine that they used to, I would say, crush recycled cans. Right? You can see there's supposed to be a can. So this is supposed to be a can. So it's they use this manual, let's say somewhere, to crush these cans when they're doing recycling. So they make it smaller and compressed, and they can just easily pack. We want to draw the free body diagram for this. Right? Let's write the problem statement. It says draw the free body diagram of the entire system. Right? Step 1. I can just use and free body diagrams of, I would say, each part, obviously not point, of the smooth, given this information smooth, so we can ignore friction, smooth piston and link, piston and link mechanism, supposed to be M, used to crush recycled cans. All right. All right. Let's just start with the entire system. All right. I'm isolating this. The entire system, the can is not part of the system, obviously, and I'm isolating this. Let's see what we got. Draw this part and then draw this part. As close as I can get this, maybe closer to this part. And we have, let me be a little fancy and use this tool there. We have the piston, right, attached to, there you go. All right, let's see what forces do we have. Well, we have one force that is external force. That's pretty straightforward. We're given that, and it's perpendicular to this surface. It's F. It's 800 newtons. What else do we have there? We have supported A, exactly, thank you, Elizabeth. So this goes like this, and this is a simple support. It's point A, it's pretty much a pin support. It's A, Y, I don't know about directions, I'll just put it there. Now here is the trick. I can write it like this, obviously. Let me just write it like this. I'll get to this. I'll get to that later. Let's assume that we don't know and just put AX and AY. What else do I have there? Pay attention to the piston. Right? It's in contact with the surface of cylinder. So I can just put one support somewhere, assuming that it's in contact, let's say at the bottom. Could be in contact at the top. You just want to take that into account. So I have to put some smooth contact. I'll call it ND. And remember that this piston is applying force to this can to crush the can. So the piston is applying force to the can. As a result, the can is applying force to the piston. Right? Newton's third law. So that comes from the can. Let's call this dx. That's pretty much it. These are all the forces for the entire system. So free body diagram for the entire system. Now let's look at each part. Each part meaning we have this handle, which is an angle 30 degrees with the horizontal line. We have link AB, and then we have the piston D. All right, let's just look at each separately. Let's look at, yes, go ahead, Sam. Dx and dy. Well, dy, where would that come from? That's the, oh, well, pay attention that I'm not separating piston from the rest. Piston is attached right now. So at point D, once I separate the piston, I'm going to have two forces. These forces that you see there, nd and dx, yeah, so it's maybe I should have called this something else. I should have called this FC. Maybe it's less confused. It's force from the can. And nd is the reaction from the surface, the smooth contact. The piston is part of the whole structure right now. Now let's separate things. Let's look at this handle itself. I'm just looking at each part now. Handle ED. I want to take that out and look at it. Let's do it like this. This is E. I'm going to put names there so things are easier to follow. B. This is A. Maybe not the best color. D. This is B. Point somewhere B, and this is point D. Now we're talking, right? Now we're talking about the connection between piston and the handle at point D. Remember, now I'm isolating this. I am isolating the handle. I'm isolating this pink line, dash line. Now let's see what we have there. Well, we have the external force is still applied on the handle. This is F. At point D, D is connected to the handle, is connected to this piston. Now, think about it this way. This piston goes back and forth when this handle moves in this direction. Right? So this handle can rotate around point D freely, right, when it pushes this way. The piston goes horizontally, but the handle can rotate at point D. So there is no resistance against couple or moment or torque there. So there is no moment reaction. If the piston was somehow preventing this from rotating, then I had to, when I removed the piston, I had to compensate for that limitation in the motion with some moment at that point. But since it can freely rotate around point D, we don't need to worry about that. But it cannot detach itself. Right? It can't go up, can't go anywhere if it's attached to this. So I have to compensate. If I take the piston out, I have to compensate for those forces. That would be dx and dy. All right. Now let's look at point B. All right, point B is hinged, or it can rotate point B if you look at link ED and link AB. So this link can rotate around point B. So there is no resistance against rotation. So I don't need to put any torque there. But it cannot move by itself. It can only move when along with link ED. So link ED and link AB are attached at point B, and because of this attachment, link AB cannot go anywhere by itself, cannot move to the right while ED is fixed. This cannot go to the right or up or any other direction. So to compensate for that limitation imposed to link AB, I have to put some forces there when I take link AB out of this system. So let's put it, you can put it in either direction, BX or BY, BX. All right. Now let's look at link AB. This is all for link ED, right? This is free body diagram for link ED. Detached it, looked at all the possible connections, compensate for the internal or external forces. Let's look at link AB. Right? That becomes more interesting. This is link AB. Right? This is point A. This is point B. Now, if I want to go with what I have, look at the free body diagram for the entire system. Point A, well, I have the, pretty much the same thing. So put AY and AX. That's the joint connection. Point B, look at the free body diagram for link ED. Well, AB is connected to link ED at point B. So whatever the force components I put on link ED at point B, I have to flip them with the same magnitude, put it at point B on link AB. So if I go with that, this should be BX and this should be BY. Now, as you see, probably the direction of BY, I did not assume it correctly based on what I see here. I have to flip it eventually when I draw the free body diagrams. But look at this link for a moment. Link AB is connected to the rest of the system and the support using 2 pins. There is no moment applied to it. Right? There is no moment anywhere because there is no resistance against rotation at either of these 2 points. And there is no external force or moment applied to link AB. What does this remind you of? A member that does not have any external force applied to it in anywhere in the middle of it. There is no torque applied to it or moment applied to it. It's just connected to other members. Yes, it's a truss. But Elizabeth, that's what I was trying to say, that if you write the free body diagram for this, if you write the equations of equilibrium for, let's say, for link AB, you're going to figure out that the direction of this is not correct. Direction of BY is not correct. You're going to get AY, not the best color. You're going to get AY is equal to minus BY, meaning that BY should be flipped. Now, once you flip BY, you have to go back and flip it on this too. So on this also should be in this direction. I intentionally.
So I like get I get like that part, like that it should be flipped, but we flip BX, and so like wouldn't you flip BY just because we flip both of them? You know what I mean?
Yeah, you're right. That's my mistake actually.
Okay.
I see what you're saying. Thank you. Thank you for pointing that out. I just made this assumption that that's the same question as before. But yeah, you're right. BY should be flipped. Thank you for pointing that out. Right? Because BY, as she said, BY is on ED is upward, so on AB should be downward. Actually, if we do that, we don't even need to correct the direction later on if we draw the free body diagram. Right? Yes, Richard, that's where I was going. So this is a 2-force member. Right? So AB is a 2-force member. It's like a truss member. So pretty much what you are gonna have, if you figured that out from the beginning, which you could, this would be AB. So get rid of a couple of unknowns. This is AB. So this would be force A, this would be force B. So you can find A and B, you're going to eliminate some unknowns. Keep in mind, then once you know this is a two force member, right, you can go back and say, well, if this is two force member and that's the direction of the force, definitely this is going to be the direction of the B, this is going to be the direction of A. As a result, the opposite of that would be on this one. And even here, A is just in this direction.